Yes.
Okay, today's subject is electromagnetic physics. Let's pass through various items. It is overview, gamma processes, charge particle processes, secondary production thresholds, physics constructors, and some user interfaces. Gamma electron transport are complicated, let's say, history, which involve gamma conversion, Compton scattering, photoelectric effect, Rayleigh scattering, gamma nuclear interaction for gammas, and ionization, Coulomb scattering, Bremsstrahlung production of lepton pair, and nuclear interaction for electrons and positrons. Although muons and hadrons have similar processes like electrons. In any type of application of Jan4, one needs to use electromagnetic physics. It is impossible to assume that you have particles because all of them have one or another electromagnetic interaction. How Jan4 is organized? There are two big sublibrary. It is electromagnetic, which are split between standard, muons, X-ray, high energy polarization, low energy DNA, adjoint, and utils. Utils include main component, which allowed you to concentrate on physics, but technical interaction between any physics, electromagnetic physics, and Jan4 kernel is located in this utils subdirectory. There is also processes optical. It is processes for transport of optical photons. We have specialization that those which are on left are useful for HEP, while low energy DNA at Adjoint is more specific sublibraries. How all these electromagnetic processes are organized? We come to coherent approach for all electromagnetic subpackages. And we need this in order to have situation when low energy and high energy models can work together. We have more or less common notation. Physics interaction of process are in process class. We usually have a name which correspond to what it is doing. For example, Compton scattering. It is process to simulate Compton scattering of gammas at atomic shells. There are three base classes: G4V EM process, G4V energy loss process, G4V multiple scattering, and all other processes from electromagnetic library inherit from these three. These three classes are responsible for interaction with the kernel and take actions which are common to all electromagnetic processes. We use so-called model approach. Idea of model is that for given process, we spoke about Compton one, we may have several models. For low energy, we may have one kind of model, for high energy another. We may choose models which are more fast, but neglecting atomic structure because at high energy it is not as important as at low energy, but we may have a more accurate model for low energy, and we can combine them together inside Compton process. For example, naming scheme is model name, process name, a model. For example, Livermore Compton model. Models are defined for energy range, although models may be defined for G4 region. And all models inherit from G4VM model-based class. Inside model classes, you have really implementation of physics. And we have formulas, we have all what is needed in order to describe details of physics processes. We Gen4 need multithreaded mode. And in order to have scalability of multithreaded mode, we do following. At initialization time of Adjoint, we prepare physics tables, which are unchanged. So they are stable during the run, and any model of this kind and any process of this kind may, from any thread, may take these values from these tables. On this cartoon, there is an organization. In the master thread, at initialization, model data and process data are produced. And then in runtime, worker threads, number of worker threads might be whatever. We do not have a limitation. They only use these data which are prepared in the beginning. They access model data, process data, and models use model data, process use process data. We have a loss table manager, which is thread local class for management of electromagnetic data. And it manages all electromagnetic classes per thread. In current version of Adjoint, we even may not have a master thread, but the first thread where we start Adjoint may be the master. And this loss table manager interact with all electromagnetic processes, with models, and processes models access data via G4EM data handler. It is data per atom, so element data registry. And also for table, it is EM data registry. It is various tables, so one-dimensional, two-dimensional data for each material are in data registry. In element data registry, usually data correspond to atomic number. In this organization, responsibility for keeping and to control the data are in these two registries, element and EM data registry. Although these two are responsible for destruction of data end of run. Now let's speak about processes. Processes, electromagnetic process may be quite complicated. For example, photoelectric effect. If gamma energy above some threshold, Gamma may interact with atomic electron, be absorbed, and the electron may be emitted from the atomic shell. At the same time, shell become with one vacancy. So after emission of photoelectric electron, there is atomic relaxation process, and extra low energy X-rays may be emitted. Or alternatively, Auger electrons may be emitted from electron shell. Primary gamma may be polarized. And if there is a polarization of primary gamma, then electron has angular distribution of electron depends on this polarization. If we compare all processes which are needed for gamma, we can see on the right picture which taken from PDG. It is gamma cross-section for carbon and for lead. In both cases, we have a low energy part where photoelectric effect dominates, and you can see shell structure of atoms in this dominated cross-section. Also, non-zero effect comes from Rayleigh scattering of low energy gamma. But at high energy, dominates electron-positron pair production cross-section, which is much more than any other. In the middle, Compton may be important, and also there is a small peak. I don't know whether my pointer can show you. It is giant dipole resonance where gamma may produce neutrons in this interaction. It is not seen in carbon in this scale of cross-section. It exists for carbon, but lower, and well seen for lead. So physics is quite rich, and we may either take into account atomic de-excitation or disable it. We have special UI commands to enable Auger electron production. If you put in your macro file this line, or even Pixia may be taken into account for gamma and electrons. Pixia, it is particle-induced X-ray emission. And by default, both processes are disabled because we don't want to have performance penalties. If you look into any default gen, for example, where verbosity level is 1, you can see this beautiful printout which tell you everything about each process. For gamma, it is photoelectric, Compton, conversion, and Rayleigh. And here is a list of models involved. There is interval of energy for which model is active. And there are some information about parameters for each process. And there is information about size of tables which are pre-built at initialization time. Here is the information about number of beams, lowest, highest energy. There is 2 models for gamma conversion at normal energies up to 80 GeV, but above 80 GeV, we have to take into account saturation due to LPM effect. About charged particles, for simulation of charged particle transport, we use condensed history approach. It means that on a step, we compute energy loss And for this computation, we also need to know range, and we need to know the delta electron production probability, Bremsstrahlung probability. And in runtime, we take tables which we pre-compute at initialization phase. We often use spline interpolation to have, let's say, more accurate cross sections and DDX. There is an important moment. If you are in condensed history approach, you need to take into account stochasticity in energy transfer from particle to media. So you need to apply energy loss fluctuation. We apply it on each step. And for that, we use interface to fluctuation model. And we have G4V EM fluctuation model based interface and implementation for more accurate, less accurate fluctuation model. And of course, production threshold is important value for each material. If atomic de-excitation is active, along step, Auger electrons and fluorescence may be produced. If we look into electrons and positrons, we immediately see that there are two main regimes. At low energy, ionization dominates. Ionization from electron and positron are not identical, but the difference is not very big. But at high energy, everything is dominated by radiation loss, so by Bremsstrahlung process. And in this sense, electrons and positrons become more equivalent. At low energy, we see significant effects from positron annihilation, and positron annihilation cross-section growing when energy of positron is reduced. And this needs to be taken into account when we make electron and positron transport. For heavier particles, beta block formula is used. We use beta block formula with number of corrections. For C, it is shell correction. Delta is density effect correction. F is final size correction, and also there are Barkas term, which has that in power 3 dependence on charge, and block term, which has dependence in the force power of electric charge of a common particle. We can apply this approach, this formula, only if energy is above 2 MeV for protons, for example. Lower, we have so big shell effects if proton go in the material, and in that case, this term with shell correction is so big that it is not practical to use beta block formula. We use parameterization of DDX based on experimental data. Proton, in some sense, for us is a key particle because we use scaling relation for heavy charged particles. There is a good scaling rule which valid for all heavy particles. Stopping power or DDX for any charged particle may be expressed via d(dx) of proton, but at energy which is different. We should multiply energy by ratio between mass of proton and other hadron. And we need, of course, multiply by electric charge of hadron squared, because proton has charge 1. So by this scaling, we may find out how to handle all hadrons, muons, ions. For muons, we also take into account radiative corrections, but the formula practically is the same. And for low energy, as I said before, we use parameterization. If at each step we sample fluctuation of energy loss in a linear scale if you measure energy loss in Zin absorber, you will see a long tail. This long tail needs to be taken into account in limit of very thin step of a particle. We call this energy loss fluctuation as Landau fluctuation, Landau tail of fluctuation of energy transfer from charged particle to medium. If we speak also in condensed history approach about multiple scattering, we take into account multiple scattering at a step. The most significant effect come to electron and positron transport. Let's look into the plot. What is shown here? Here is energy deposition in aluminum when normally to aluminum slab you send electron of 0.521 MeV electron. R0 is a range of electron which you compute from d(dx). So it is so-called direct, it is a true range of electron which you may compute during this integration. And on the plot, we see energy deposition as function of the position within this slab. And in units of distance divided by this range computed as integral over d(dx). And we see that practically no one electron can come through this slab and have direct coordinate equal to 1. It happens because of elastic scattering of electron within this material. There are many scatterings, and maximum energy deposition is somewhere on 0.25 from the range of electrons. So trajectory is very very stochastic. And the different Janfo models predict this with different accuracy, but in this plot, all they are decent, and they reproduce experimental data well. But the code of multiple scattering is quite complicated. If you do a step, you need sample scattering angle at the step and transverse displacement. You need to have this coherent sampling of these two values for any size of a step, for any primary particle which come in. And you may do this only if you put some limitation step. It is why important parameter for multiple scattering is algorithm of step limitation. We have four kind of step limitation for multiple scattering. Simple, use safety. Safety is geometry distance to closed boundary. Safety plus is alternative method to limit the step. And finally, use distance to boundary. The last one has sense if you have no magnetic field, then you may estimate direct distance to the boundary from pressed point to point when you will have intersection. And you may apply some step algorithm which use 5 parameters: range factor, geometry factor, safety factor, skin, lambda limit. And you have different combination of values for different types of step limitation. If we go to describe positron annihilation, we have possibility to annihilate into 2 or 3 gamma on fly and at rest. Again, we introduce different options because for HAP application, we may not so, for us, maybe not so important to have precise 3 gamma annihilation, which has low cross-section. We may use parameter lowest triplet energy. In this case, it is proposed to be 10 MeV. There are different options to sample creation and decay of positronium. We have 4 variants, and we may define the model which you need in your application. The probability to create para or orthopositronium depends on material. For material, you may define these parameters which come from experimental data and have more accurate simulation for these kind of events. We have possibility to simulate quantum correlation. Usually, Monte Carlo simulation take one particle, one track, and propagate it until it is killed. But we have example of physics. For positron annihilation, 2 gammas have correlated polarization planes. And then when these gammas are in your tomograph, for example, there is Compton scattering. And Compton scattering provides electrons with direction which depends on what is polarization of a given gamma. It is shown that we can simulate this quantum correlation, and we, for the first time, for Monte Carlo tools, implement this in our code, and it is potentially possible. Secondary production thresholds. Secondary production thresholds. Let's discuss it on example of Bremsstrahlung. I also mentioned this yesterday, and let's discuss today. We subdivide energy spectrum on final particles on 2 parts. One part which shown on plot in green is continuous energy loss. And the formula for that is shown below. dx can be computed as integral of energy from 0 to production threshold of this energy transfer. Above cut value, we produce real gammas for further tracking. And in that case, we need compute not dx, but cross-section, which called a restricted cross-section, and we make integral of differential cross-section from cut value to maximum. For gamma, maximum value is energy of primary particle, kinetic energy of primary particle. So we implement this mechanism. We have cut different in each material, and we either account energy deposition as continuous energy loss or produce direct gammas. Default cut in Adjoint is historically, there is no big sense, but historically it is 0.7 millimeter. But a user may define via UI command, there are simple commands, set cut 0.1 millimeter. It is possible to set cut for given particle, for given region. And also it is possible to limit production threshold, set low H. In this case, it is 500 electron volts instead of 1 keV, which is the default. But you need to understand that it is important, but not mandatory. It is possible to work without cut. How to use cuts in your applications? There is a simple example. If electron of 45 MeV transfer silicon slab of 5 micron, what cut one need to establish? On the left plot, there is dependence of mean energy deposition in silicon as function of cutting range. It turned out that if you increase cutting range, you start to get wrong and wrong results after some value, which is around 5 micron. So if you put cutting range larger than your sensitive volume, you overestimate energy deposition inside because you integrate in DDX energy, which in reality leave this silicon layer. And here is a good example which shows that there is a golden rule. You need, for accurate simulation, set a cut which is lower than thickness of sensitive layers in your setup. Electromagnetic physics constructors. Electromagnetic physics have different components. Electromagnetic particles are gamma, electron, positron, muons, pions, kaons, hyperons, and also heavy particle like tau, lepton, BD, BS, lambda C, sigma C, and so on. There are light ions and generic ions. There is 12 light hyperions and anti-hyper nuclei. And we need for all of them define processes. For gamma, of course, it is specific, but for charged particles, it is ionization, Bremsstrahlung, all these things. As we discussed before, we define this in physics list, and we prefer to use modular physics list and define electromagnetic physics via G4V physics constructor interface. For HEP applications, we have 3 options. G4EM standard physics is our default. It included in many physics lists which are in Adjoint for distribution. And for example, Atlas and some other experiments use directly this EM standard physics. There is electromagnetic physics option 1, which is a bit faster than default, because in this option 1, we configure parameter apply cut for gamma processes. We use gamma general. We use simple multiple scattering step limitation. And if you look into our distribution, this physics list is called FTFP by EMV. Why V, I don't know. Even it is historically we put V as a first. V correspond to option 1. And physically which close to this option 1 used by CMS experiment at CERN. LHCb experiment use specific physics list, and option 2 is similar to option 1, but it has the same configuration as LHCb is using. And we called such physics list FTFP by EMX. For other applications, for example, for medical, for space, for other applications, we may consider alternative physics lists. There are EM option 3 and 4. For our favorite, it has error-free multiple scattering model, which called Goldsmith-Sanderson model, GS model. And the physics list is called FTFP bar TMZ. We combine in this configuration the most accurate known electromagnetic models. For example, internally there is Penelope ionization for low energy, Livermore gamma processes. There are other special definition. We try to be much more accurate as much as we can, but this list is slowest. Some compromise with relatively good accuracy, but less CPU demanding is option 3. We use urban multiple scattering model in that case, but with parameters of step limit, which allow to have reasonable overall accuracy. And this list is recommended for a simulation of proton ion therapy. There is also two physics lists, Livermore and Penelope, use a different low energy model. And we recommend them for cross checks of option 4 and option 3 variants of electromagnetic physics. There are extra physics constructor in the distribution. For example, SS, it is single scattering instead of multiple scattering. Elastic scattering is much more precise, but simulation is much more slow because all particles do each elastic collision separately. And of course, in some cases, you may have interest to run this physics list, but in general, you may have not one, but 2 order of magnitude slowdown of your application. There are special physics lists to test polarized gamma transport. Although they may be used in special circumstances. Extra experimental constructors are available in Gen4 examples. And some physics lists are custom, for example, they not all Gen 4 examples use physics list from Gen 4 library. We strongly recommend, nevertheless, when you, especially when you start to learn, begin from reference physics list. Try default, try option 4, try think what you like, what you don't like, and then maybe choose some intermediate physics list. And after that, to think how you may configure your physics to be effective and to implement all what you need in your application. For example, we have a possibility that electromagnetic models are defined per region. There are UI commands on the bottom at pi region. So a model which is accurate. Pi provide very good sampling of fluctuations, may be very useful for gaseous detector. You define your region and apply pi models there. You may apply even DNA models there. Or microelect, it is another model which is very precise, but quite slow. And we are going to the end. We have parameters which allowed you to make extra configuration on top of physics list which we have. And there are different parameters. The most important on this slide is on the bottom. Full list of UI command and C++ interfaces is shown in application developer manual. This manual is maybe written very, let's say, in condensed manner, but there are all commands which you may use. And there are some minimal explanation of what you may achieve with different UI commands. And you may have interest to look into this manual. There are a number of helper classes which you may use and may not use in your application. It is a choice of user. It is G4EM calculator, G4EM parameters, G4EM saturation to implement Birk's effect, G4 electron ion pair. It is sampling of ionization clusters in gaseous or silicon detector. You may want to apply. Usually these helper classes are used in user actions. EM configurator is used to configure model per region. And there is also so-called NIL calculator. It is a class which helps to compute non-ionized energy loss. It is needed when you study radiation damage due to electromagnetic or nuclear processes for your electronic devices, for example. And to compute this, you may use NIL calculator again in your user actions. And in this slide, it is shown how to use G4EM calculator to compute DDX or for example, cross-section. For that, access to data from Gen 4. All what you need is instantiate physics list and initialize physics list. You don't need to do real simulation. You may apply one event simply to be sure that everything is working. And then you may study what are cross-sections, what are DDX. And here is one of examples. And you may have a look in example, extended electromagnetic test scheme 0. And finally, there is DNA project, which I emit. It is a project which is intended to simulate effect of radiation on human body. And it has physics stage, then physicochemical stage, when radicals and salvated electrons are produced. Then there is transport of these chemical components. There are complicated models of DNA strands, chromatin fibers, chromosomes, and so on. And you may either simulate direct DNA damage by radiation or indirect damage when you simulate chemistry. Finally, you need to apply some elements of biophysics, because some biological molecule can repair or can be broken. So this is quite a big picture connecting human being. Thank you. Any questions?
Hi, Vladimir. Thank you. There was one question online. I hope that we might be able to have a bit of time after the break with you, because we had some questions yesterday, and we'll have to take a break now here shortly. The question online had to do with the density effect, and a user found an exception with the Sternheimer factor related to the density correction beta block, but they said that it was in a case for a quote-unquote perfect detector with very high density, which seemed to me to be an issue that's recognized in this exception. Do you,
in any case, if there is exception in your run, exception is you even do not go to forum. You go directly to Bugzilla bug report. You describe how you achieve this, and we will try to fix. For density effect computation, we have basically two approaches. One is parameterization of Sternheimer tables, and we have also alternative approach when it is possible to compute directly on fly density effect by solving transient equation. There are, if you have very dense material, of course, there are exponents within formulas. And if argument of exponent is too big, there may be some problem. But we cannot know this in advance. We have great statistics when we work with Atlas CMS, and there were no problem. If in your case you have this, please make Bugzilla bug report with numbers, and we will try to help to make protection for this particular case.
Okay, thank you, Vladimir. So I hope you can join us in the section afterwards. As I said, there are questions from yesterday that touch on electromagnetic physics as well, but we need to take, for practical organizational reasons, we need to take the coffee break now. So can we start at 10 minutes to the hour? So in about 17, 18 minutes, please all.